Listening Practice, Chapter 1, Introduction to Modern Transportation 1.1 The evolution of mobility, from horsepower to electric propulsion. Transportation has undergone a radical transformation, driven by humanity's quest for speed, efficiency, and sustainability. Early innovations, pre-industrial era, reliance on animal power, horses, camels, and wind, sailing ships. Steam revolution, James Watt's steam engine, 1775, enabled railways and steamships, shrinking travel time and fueling industrialization. Internal combustion dominance, Model T, 1908 Henry Ford's assembly line democratized automobiles, but fossil fuels entrenched environmental costs. Jet age, 1950s commercial aviation expanded global connectivity, albeit with high carbon footprints. Electric resurgence, modern EVs, Tesla's Roadster, 2008, reignited interest in electric propulsion, leading to today's 26 million EVs globally, IEA, 2023. Aviation shift, Eviation Alice's 2022 maiden flight showcased all-electric regional air travel, targeting 440-mile ranges. Challenges, battery energy density, charging infrastructure gaps, and life cycle emissions of lithium-ion tech. 1.2 Key drivers of innovation, sustainability, urbanization, and technology. Three forces are reshaping transportation's future. 1. Sustainability, climate imperatives. Transport accounts for 24% of global CO emissions, EPA. Zero-emission mandates, e.g., EU's 2035 ICE ban, push EV adoption. Circular economy, companies like Redwood Materials recycle EV batteries, reducing reliance on mined resources. 2. Urbanization, megacity pressures. By 2050, 68% of the global population will live in cities, UN, demanding solutions like Hyundai Supernal eVTOL air taxis to decongest roads. Micromobility, e-scooters and bike sharing, e.g., Lime, Bird, bridge last-mile gaps in dense urban cores. 3. Technology, battery advances. Solid-state batteries promise 500-plus mile ranges, Toyota, 2030. Autonomous systems, Waymo's robo-taxis in San Francisco and Tesla's FSD Beta highlight AI's role in safety and efficiency. Digital integration, IoT-enabled smart traffic systems reduce congestion in cities like Singapore. Case study, Norway's EV adoption, 90% of new car sales, stems from tax breaks, charging networks, and renewable energy synergy. 1.3 Public versus private sector roles in transportation. The transition to sustainable mobility hinges on collaboration and competition between governments and corporations. Public sector, policy frameworks, subsidies, U.S. Inflation Reduction Act, $7,500 EV tax credits. Regulation, China's NEV mandate requires automakers to produce 40% EVs by 2030. Infrastructure, EU's TEN-T program funds cross-border EV charging and rail networks. Private sector, automakers, GM's $35 billion EV investment, 2020-2025, targets 30 global models, while Rivian's Amazon van fleet redefines logistics. Tech disruptors, startups like Joby Aviation, Evtools, and Einride, autonomous freight, challenge legacy players. Collaborative models, smart cities, Sidewalk Labs Toronto project, scrapped in 2020, aimed to integrate autonomous shuttles and data-driven transit. Public-private partnerships, PPP's Los Angeles Urban Movement Labs tests mobility innovations like curbside EV charging. Tensions, equity, rural versus urban infrastructure investment divides. Data privacy, autonomous systems reliance on user data sparks regulatory debates. Chapter 1 Summary Modern transportation is a tapestry woven from historical leaps, urgent climate action, and technological disruption. From steam engines to Evtools, each innovation reflects societal needs and challenges. As public policies and private ventures race toward decarbonization, the path forward demands balancing ambition with equity, ensuring mobility's future is not just greener, but inclusive. The following chapters delve into the vehicles, policies, and visions propelling this transformation. Key takeaways: evolution, fossil fuel dominance is yielding to electric and autonomous tech. Drivers, climate urgency, urban density, and tech breakthroughs shape innovation. Collaboration, public-private synergy is critical for scalable, equitable solutions. Next, Chapter 2 explores historical milestones and ethical debates that set the stage for today's mobility revolution. Chapter 2, Historical Foundations of Transportation 2.1 From Steam Engines to EVs, A Timeline of Breakthroughs 1. 1769, James Watt patents the steam engine, revolutionizing transportation with steam-powered trains, 1804, and ships, 1807. 1886, Carl Benz invents the first gasoline-powered automobile, the Benz patent motor wagon. 1908, Henry Ford introduces the Model T, mass-producing affordable cars via assembly lines. For early 20th century, electric vehicles, EVs, like the Baker Electric, 1899, gained popularity but declined due to limited range and ICE dominance. 1970s oil crises spark renewed interest in alternative energy, leading to prototypes like the GM EV1, 1996. 1997, Toyota Prius debuts as the first mass-produced hybrid, bridging ICE and electric tech. 2008, Tesla Roadster revitalizes EVs with lithium-ion batteries, achieving 245 miles per charge. Key insight: each breakthrough addressed societal needs, speed, affordability, and sustainability while setting the stage for modern EVs. 2.2 The Rise of Electric Vehicles, 2000s Present, 1. Technological advancements, battery innovation, lithium-ion batteries, e.g., Panasonic Tesla Gigafactory, reduce costs by 89%, 2010-2021. Regenerative braking, enhances efficiency by recapturing energy. 2. Policy drivers, subsidies, U.S. tax credits, $7,500, and EU emissions regulations push automakers toward EVs. Global targets: Norway aims for 100% zero-emission car sales by 2025, California bans ICE sales by 2035. 3. Market expansion, Tesla dominance, Model S, 2012, and Model 3, 2017, redefine luxury and affordability. Legacy automakers, Ford Mustang Mach-E, 2020, and Volkswagen ID.4, 2021, signal industry-wide shifts. Global players, BID, China, and NIO lead in Asian markets with battery swapping tech. Case study: Tesla's 2020 Battery Day unveils plans for a $25,000 EV, accelerating mass market adoption. 2.3 Ethical debates, environmental impact and labor shifts. 1. Environmental trade-offs, battery production, mining lithium, cobalt, and nickel raises concerns about resource depletion and pollution. Carbon footprint, EVs reduce tailpipe emissions by 68%, Union of Concerned Scientists, but manufacturing impacts vary by energy source. 2. Labor market transformation, job displacement, transition from ICE components, e.g., transmissions, to batteries and software risks 30% of auto jobs, McKinsey. Reskilling initiatives, GM's $35 million retraining program prepares workers for EV assembly and battery plants. 3. Ethical sourcing, cobalt controversy, 70% of cobalt is mined in the DRC, with reports of child labor. Companies like Tesla commit to ethical supply chains via blockchain tracking. Global perspective, EU's proposed battery passport mandates transparency in material sourcing, while the U.S. Inflation Reduction Act ties subsidies to domestic production. Chapter Summary: The evolution from steam engines to EVs reflects humanity's pursuit of efficiency and sustainability. While innovations like Tesla's batteries and BID's affordability democratize clean transport, ethical challenges from cobalt mining to labor shifts demand holistic solutions. Policymakers, corporations, and societies must collaborate to ensure the EV revolution is equitable and environmentally just. Key takeaways: technological momentum, battery advancements and policy incentives drive EV adoption. Ethical complexity, balancing environmental gains with supply chain ethics and workforce transitions. Global collaboration, cross-border policies and corporate accountability are critical for sustainable mobility. Next, Chapter 3 explores electric aviation, featuring pioneers like Aviation Alice and Hyundai Supernal eVTOL. Chapter 3, Electric Aviation, Revolutionizing Air Travel. 3.1 The Science of Electric Aircraft. Electric aviation aims to decarbonize air travel by replacing fossil fuel engines with battery-powered propulsion. However, this transition hinges on overcoming two critical challenges: battery limitations and aerodynamic efficiency. 3.1.1 Battery technology and energy density challenges. Energy density comparison: jet fuel, 12,000 Wh/kg, lithium-ion batteries, 2,300 Wh/kg. Even cutting-edge solid-state batteries, projected 500 Wh/kg by 2030, lag far behind fossil fuels. Key battery types: lithium-ion, dominates current EVs and aircraft, e.g., Tesla-inspired packs in electric planes. Solid-state, promises higher energy density and safety, e.g., QuantumScape's partnerships with aviation startups. Hydrogen fuel cells, emerging as a hybrid solution for longer ranges, e.g., ZeroAvia's 19-seat prototype. Challenges: weight, batteries account for 40% of an electric aircraft's weight, limiting payload and range. Charging infrastructure, few airports have high-power charging stations, rapid charging tech is still experimental. Thermal management, preventing overheating during high-demand phases, takeoff, climbing. 3.1.2 Lightweight materials and aerodynamic design. Materials: carbon fiber composites, reduce airframe weight by 20–30%, used in Aviation Alice's structure. Advanced alloys, aluminum-lithium alloys balance strength and weight for wings and fuselage. 3D printed components, GE Additive's printed parts optimize complex geometries while saving weight. Aerodynamic innovations, distributed electric propulsion, DEP. Multiple small motors improve efficiency and redundancy, e.g., NASA's X-57 Maxwell, laminar flow wings, smooth surfaces reduce drag, extending range, used in Alice *S design. Blended wing bodies, experimental designs, e.g., Airbus ZEROE, merge wings and fuselage for efficiency. 3.2 Case studies in electric flight. 3.2.1 Aviation Alice, maiden flight, 2022, and the future of regional air mobility. Aircraft specifications: range, 440 nautical miles, 814 kilometers, on a single charge. Capacity, 9 passengers plus 2 crew. Battery, lithium-ion packs, 820 kWh capacity. Speed, 260 knots, 480 km per hour, comparable to turboprops. Milestones: September 2022, successful 8-minute maiden flight in Washington State, reaching 3,500 feet. 2023, secured pre-orders from DHL, 12 cargo planes, and Cape Air, 75 commuter aircraft. Impact on regional mobility: targets underserved routes, e.g., Boston to Martha's Vineyard, 20-minute flight versus 2-hour ferry. Reduces operating costs by 70% compared to traditional turboprops, no jet fuel, fewer moving parts. Challenges: certification, FAA Part 23 certification delayed to 2025 due to rigorous battery safety tests. Infrastructure, partnering with Clay Lacy Aviation to install chargers at regional hubs. Competitive landscape, Hart Aerospace ES-30, hybrid electric plane, 30 seats, 500 km range, targets similar markets. Beta Technologies, developing ALIA eVTOL and CTOL aircraft for cargo and medical transport. Chapter Summary: Electric aviation, exemplified by Aviation Alice, represents a paradigm shift towards sustainable air travel. While battery energy density and certification hurdles remain significant barriers, innovations in materials and aerodynamics coupled with growing demand for regional connectivity signal a promising future. Success hinges on advancing battery tech, expanding infrastructure, and fostering regulatory collaboration. As the industry evolves, electric aircraft could soon redefine short-haul travel, offering quieter, cleaner, and cost-effective alternatives to conventional planes. Key takeaways: battery limitations. Energy density must triple for electric planes to compete with jets on long routes. Design innovations. Lightweight composites and DEP systems are critical to maximizing efficiency. Regional focus. Short-haul flights, under 500 miles, are the near-term sweet spot for electrification. Next, Chapter 4 explores urban air mobility, UAM, and Hyundai Supernal eVTOL, expanding on the convergence of aviation and urban transit. Chapter 4, Urban Air Mobility, UAM. The rise of EVTOLs. 4.1 Engineering EVTOLs, electric vertical takeoff and landing vehicles. EVTOLs are electric aircraft designed for vertical takeoff and landing, enabling efficient urban transport without traditional runways. Their engineering focuses on balancing performance, safety, and noise reduction for seamless integration into cities. 4.1.1 Propulsion systems, rotors, duct fans, and hybrid designs. Multi-rotor systems, design, multiple small propellers, 612, for vertical lift, similar to drones. Pros: redundancy, safety if one rotor fails, precise control. Cons: higher noise levels and energy consumption. Example, EHang 216, China, with 16 rotors for autonomous passenger transport. Duct fan systems, design, propellers enclosed in ducts to enhance thrust efficiency and reduce noise. Pros: quieter operation, improved safety, reduced exposed blades. Cons: heavier structure, reduced agility. Example, Lilium Jet, Germany, using 36 duct fans for whisper quiet flights. Hybrid designs, tilt rotor/wing, rotors tilt horizontally for forward flight, combining vertical lift with fixed wing efficiency. Pros: longer range, 200 plus km, energy efficient cruise. Cons: mechanical complexity. Example, Joby Aviation S4, USA, with 6 tilt rotors for 240 km range at 320 km per hour. 4.1.2 Noise reduction and urban integration, noise mitigation, blade design, curved or serrated edges, e.g., Joby's propeller tech, reduce turbulence and noise to 45 dB, quieter than a conversation. Operational strategies, flight paths: avoid residential zones, altitude management during takeoff/landing. Urban infrastructure, vertiports, modular hubs for charging, maintenance, and passenger boarding, e.g., Skyports in Los Angeles and Hyundai Supernal vertiport concept. Air traffic management, AI-driven systems, e.g., NASA's UAM Grand Challenge, coordinate EVTOLs with drones and helicopters. Regulations, FAA's Advanced Air Mobility, AAM, Initiative and EASA's SCVTOL certification framework guide safe operations. 4.2 Case Studies in eVTOL Development. Case Study 1, Hyundai Supernal eVTOL, Design, Hybrid electric propulsion with 8 rotors for vertical lift and a fixed wing for cruise efficiency. Noise reduction, duct rotors and optimized blade pitch for 65 dB during takeoff, comparable to background traffic. Urban integration, partners with Uber Elevate for app-based booking and plans vertiports atop parking garages. Target, 2028 commercial launch in cities like Miami and Los Angeles. Case Study 2, Joby Aviation S4, propulsion, 6 tilt rotors enable vertical takeoff and 320 km per hour cruise speeds. Noise, 45 dB at 500 feet altitude, audible but not disruptive. Certification, FAA Part 135 Certification, 2023, for air taxi operations, testing in NYC and San Francisco. Range, 240 kilometers, ideal for urban-suburban routes, e.g., San Francisco to Napa Valley. Case Study 3, Archer Midnight, design, 12 rotors with a 12 tilt 6 configuration, 6 rotors tilt for forward flight. Noise, 50 dB at 2,000 feet, achieved via proprietary sound dampening materials. Partnerships, United Airlines plans to deploy 200 aircraft for airport to city center routes by 2025. Chapter Summary: EVTOLs are redefining urban mobility through innovative propulsion and noise reduction technologies. Hybrid systems like Joby's tilt rotors and Hyundai's duct fans balance efficiency with urban compatibility. However, success hinges on robust vertiport infrastructure and adaptive regulations. As cities like Los Angeles and Seoul pilot air taxi networks, EVTOLs promise to alleviate ground congestion while setting new standards for sustainable urban transport. Next, Chapter 5 explores autonomous and connected vehicles, delving into self-driving tech and ethical challenges. Chapter 4, Urban Air Mobility, UAM: The Rise of EVTOLs. 4.2 Case Studies in eVTOL Development. 4.2.1 Hyundai Supernal eVTOL, Prototype Testing and Urban Air Taxi Vision, 2023. Hyundai Supernal, a subsidiary of Hyundai Motor Group, is advancing its eVTOL ambitions with a focus on urban integration and accessibility. Prototype Testing, 2023, Design, Hybrid Electric Propulsion System with 8 rotors for vertical lift and a fixed wing for efficient forward flight. Noise levels, achieved 65 dB during takeoff, comparable to background traffic noise, using duct rotors and optimized blade design. Range, 6,100 km, 3,762 miles, on a single charge, targeting short urban-suburban routes, e.g., JFK Airport to Manhattan. Urban Air Taxi Vision, vertiports, modular hubs integrated into existing infrastructure, e.g., parking garages, rooftops. Partnered with Uber Elevate for seamless app-based bookings. Target cities, pilots planned in Los Angeles, Miami, and Seoul by 2026, with a commercial launch by 2028. Sustainability, aims to use 100% renewable energy for charging and explore hydrogen fuel cells for longer ranges. Partnerships, collaborates with NASA on air traffic management systems. Join the AAM coalition to shape U.S. policy for eVTOL integration. 4.2.2 Joby Aviation's FAA-certified air taxi network. Joby Aviation, a leader in eVTOL development, achieved critical FAA milestones in 2023, paving the way for commercial operations. FAA certification, Part 135 Air Carrier Certificate, granted in 2023, allowing Joby to operate air taxi services. Type certification progress, finalizing testing for its 5-seat tilt-rotor eVTOL, targeting FAA approval by 2025. Air Taxi Network, initial routes, New York City, Manhattan to JFK, 12 minutes versus 1 hour drive, and Los Angeles, downtown to Santa Monica. Partnerships, Delta Airlines, integrating Joby's service into Delta's app for last-mile airport transfers. Toyota, manufacturing support to scale production to 500 aircraft annually by 2026. Aircraft performance, speed, 200 miles per hour, 322 kilometers per hour, cruise speed. Range, 150 miles, 241 kilometers, on a single charge. Noise, 45 dB at 1000 feet, quieter than a dishwasher. 4.3 Economic and social implications. 4.3.1 Reducing traffic congestion in megacities. EVTOLs promise to decongest roads by shifting short-haul trips to the skies. Case study: Sao Paulo, helicopters already handle 500+ daily flights among the wealthy. EVTOLs could democratize this for $3.5 per mile by 2030, Morgan Stanley. Projected to reduce rush hour traffic by 10–15% in cities adopting UAM. Economic impact, time savings. A McKinsey study estimates EVTOLs could save urban economies $100 billion annually by 2035 through reduced congestion. Job creation, vertiport construction, maintenance, and air traffic management could create 300,000 plus jobs globally by 2040. 4.3.2 Public acceptance and safety concerns. Public trust remains a hurdle for widespread eVTOL adoption. Safety, redundancy. Joby's 6 independent rotors ensure safe landing even if 2 fail. Certification, rigorous FAA crash testing and battery safety protocols, e.g., thermal runaway mitigation. Public perception, surveys. Only 35% of urban residents feel comfortable with EVTOLs, 2023 Deloitte report, citing noise and privacy concerns. Noise mitigation, Supernal's duct fans and Joby's propeller tech aim to keep noise below 65 dB, aligning with WHO guidelines. Equity, critics warn EVTOLs may initially cater to elites. Hyundai and Joby propose subsidized fares for essential workers in partnership with cities. Chapter summary: Hyundai Supernal and Joby Aviation exemplify the race to dominate urban skies, blending cutting-edge engineering with strategic partnerships. While EVTOLs could slash congestion and unlock economic gains, success hinges on safety, transparency, noise reduction, and equitable access. As cities like LA and Seoul pilot these systems, public acceptance will determine whether UAM becomes a transformative tool or a niche luxury. Key takeaways: Hyundai Supernal prioritizes urban integration and renewable energy for short hop routes. Joby Aviation leads in FAA certification and scalability, targeting airport transfers. Challenges: balancing innovation with public trust and affordability. Next, Chapter 5 explores autonomous ground vehicles and their ethical dilemmas. Chapter 5, Autonomous and Connected Vehicles. 5.1 Self-driving technology, LiDAR, AI, and sensor fusion. Autonomous vehicles, AVS, rely on 3 core technologies to perceive and navigate their environment. 1. LiDAR, light detection and ranging, uses pulsed lasers to create 3D maps of surroundings with centimeter-level precision. Key players: Luminar, used by Volvo, Mercedes, and Velodyne, pioneer in automotive LiDAR. Limitations: high cost, $10K $75K per unit, and performance degradation in heavy rain/snow. 2. AI and machine learning, neural networks process data from cameras, radar, and LiDAR to identify objects, e.g., pedestrians, traffic lights. Training data: Waymo's CarCraft simulation platform logs 20+ million virtual miles daily. 3. Sensor fusion, combines inputs from cameras, Tesla, radar, Mobileye, and LiDAR, Cruise, for redundancy. Edge cases, handling ambiguous scenarios, e.g., faded lane markings, emergency vehicles. 5.2 Case studies. 5.2.1 Waymo's robotaxi expansion, progress, operates fully driverless taxis in Phoenix, AZ, and San Francisco, CA, 2023, with plans for Los Angeles and NYC. Fleet, 700+ Jaguar I-Pace vehicles, 24/7 service in geofenced areas. Safety metrics: 0.41 disengagements per 1,000 miles, versus 3.2 for Cruise in 2023. Partners with UPS and Walmart for autonomous deliveries. Challenges: limited operating zones, geofencing, and high sensor costs, $200K per vehicle. 5.2.2 Tesla's full self-driving, FSD, beta challenges, technology, relies on 8 cameras and AI, no LiDAR/radar, with vision-only approach. FSD Beta 1.4.4, 2023 Enhanced lane changes and pedestrian detection. Controversies, NHTSA investigations, 40-plus crashes involving Tesla Autopilot, 16 fatalities since 2016. Misleading marketing, FSD still requires driver supervision, despite the name. Adoption, 400,000 plus FSD beta testers, 2023, with subscription model, $199/month. 5.3 Ethical dilemmas, decision-making algorithms and liability. 1. The trolley problem reimagined, how should AVS prioritize lives in unavoidable crashes? MIT's Moral Machine study found global cultural biases, e.g., Westerners prioritize young over elderly. Real-world impact, Mercedes' 2023 decision to prioritize driver/passenger safety sparked backlash. 2. Liability and regulation, legal gray areas, is the manufacturer, e.g., Tesla, software developer or human operator liable in crashes? EU's 2023 AI Act mandates AVS to log decision-making data for accountability. Insurance shifts, policies increasingly target manufacturers, e.g., GM's Cruise insures its fleet. 3. Transparency and trust, black box algorithms, most AV systems lack explainability, raising public skepticism. Volvo's approach, publishes ethical guidelines for its AVS, emphasizing transparency. Chapter Summary. Autonomous vehicles represent a seismic shift in mobility, blending LiDAR, AI, and sensor fusion to redefine transportation. While Waymo leads in safety and scalability, Tesla's FSD beta highlights the risks of rapid public deployment. Ethical dilemmas from algorithmic bias to liability battles underscore the need for global standards and transparent AI. As AVS inch closer to ubiquity, society must grapple with a fundamental question: can machines be trusted to make life and death decisions? Key takeaways: tech divide, LiDAR versus camera-only approaches reflect competing philosophies, safety versus cost. Regulatory lag, policies struggle to keep pace with AV advancements. Ethical imperative, transparent AI and standardized ethics frameworks are critical for public trust. Next, Chapter 6 explores Hyperloop and high-speed rail innovations, from vacuum tubes to maglev trains. Chapter 6, Hyperloop and high-speed rail. 6.1 The Hyperloop concept, vacuum tubes and magnetic levitation. The Hyperloop is a futuristic transportation system conceptualized to move passengers and cargo at near supersonic speeds through low-pressure tubes. Key components: vacuum tubes, reduced air pressure minimizes friction, enabling speeds of 701,200 km/h, magnetic levitation, maglev pods levitate above tracks using electromagnetic forces, eliminating wheel-rail friction. Propulsion, linear electric motors accelerate pods, with solar panels often proposed for energy sustainability. Advantages over traditional rail: speed, faster than conventional high-speed trains, e.g., Japan's Shinkansen at 320 km per hour. Energy efficiency, lower energy consumption per passenger due to reduced air resistance. Weather resistance, enclosed tubes protect against weather disruptions. Challenges, safety concerns, rapid decompression risks in tube breaches. Infrastructure cost, estimated $2,100 million per mile, depending on terrain. 6.2 Global projects. 6.2.1 Virgin Hyperloop's India Corridor, Vision, a proposed 1,400 km route linking Mumbai and Pune, reducing travel time from 3.5 hours to 25 minutes. Progress, 2018, Maharashtra government declared Hyperloop a public infrastructure project. 2020, Virgin Hyperloop completed first passenger test in Nevada, reaching 172 km per hour. 2023, Project stalled due to funding gaps and regulatory hurdles, Virgin shifted focus to freight. Unique aspects, aim to integrate with Mumbai's metro system for seamless urban-suburban transit. Proposed cargo pods to decongest India's truck-dominated freight network. 6.2.2 China 600 km per hour maglev trains, technology, electromagnetic suspension, EMS uses superconducting magnets for levitation and propulsion. Speed, 600 km per hour, tested in 2021, the world's fastest ground transport. Deployment, Shanghai maglev, operational since 2004, 30 km route 430 km per hour. Qingdao prototype, unveiled in 2021, plans for a Beijing-Shanghai line, 1,300 km in 3.5 hours. Strategic goals, reduce domestic flight demand and carbon emissions. Export maglev tech to Southeast Asia and Europe. 6.3 Feasibility and cost-benefit analysis, Hyperloop, pros, potential to disrupt long-haul travel with ultra-high speeds. Modular design could lower urban sprawl. Cons, unproven at scale, no commercial systems operational. High upfront costs and land acquisition challenges. Cost, estimated $5,100 million per mile versus high-speed rail's $2550 million per mile. Maglev, pros, proven tech, e.g., Shanghai's operational line. Lower maintenance than wheeled trains. Cons, $6,100 million per mile construction cost. Limited interoperability with existing rail networks. Environmental impact, Hyperloop, solar-powered potential, but energy-intensive vacuum maintenance. Maglev, lower emissions than air travel but reliant on grid energy sources. Market viability, Hyperloop, likely niche, e.g., specific freight corridors, until safety and funding improve. Maglev, expanding in dense corridors, e.g., China, Japan, but limited by cost. Chapter summary. While Hyperloop remains a visionary concept hampered by technical and financial barriers, maglev trains like China's 600 km per hour system demonstrate the potential of high-speed rail. Both promise to redefine long-distance travel but face stark trade-offs, Hyperloop's unproven scalability versus maglev's prohibitive costs. Success hinges on government support, technological refinement, and public-private collaboration. As climate urgency grows, these systems could complement, not replace, traditional rail and air travel, offering sustainable alternatives for the 21st century. Key takeaways: Hyperloop, high risk, high reward with transformative speed but unproven viability. Maglev, expensive yet reliable, ideal for dense, high-demand corridors. Sustainability, both systems require green energy integration to meet climate goals. Next, Chapter 7 explores sustainable ground transportation, from electric trucks to micromobility solutions. Chapter 7, Sustainable Ground Transportation 7.1 Electric Trucks and Freight Innovation. The freight industry, responsible for 7% of global CO emissions, is undergoing a seismic shift toward electrification and alternative fuels. This section explores advancements in electric and hydrogen-powered trucks reshaping logistics. 7.1.1 Tesla Semi and Rivian's Amazon fleet. Tesla Semi, specifications, range, 500 miles, 800 kilometers, on a single charge, semi-long range. Battery, 1 mWh capacity, powered by Tesla's 4,680 cells. Charging, Megacharger delivers 70% charge in 30 minutes. Milestones, 2022, first deliveries to PepsiCo for Frito-Lay routes in California. 2023, Walmart and UPS expand orders for regional freight. Impact, reduces per mile costs by 25% versus diesel trucks, Tesla claims. Targets 1 million miles of durability with regenerative braking. Challenges, limited megacharger network, only 10 stations in the US as of 2023. High upfront cost, $180,000 versus $120,000 for diesel. Rivian's Amazon fleet, design, EDV 700, all-electric delivery van with 150-mile range. Features, sensor-driven safety systems, 3,500 pounds payload capacity. Deployment, 2023, 10,000 plus Rivian vans deployed across 1,800 U.S. cities. Amazon's goal, 100,000 vans by 2030, eliminating 4 million tons of CO annually. Innovation, route optimization via machine learning to minimize energy use. Bidirectional charging powers onboard tools, e.g., refrigerators. 7.1.2 hydrogen fuel cell trucks, e.g., Hyundai Scient fuel cell, technology, hydrogen tanks, 7 tanks storing 32 kilograms of hydrogen. Range, 450 miles, 725 kilometers, refueled in 820 minutes. Output, 350 kilowatts fuel cell system paired with a 72 kilowatt-hour battery. Deployment, Europe, 47 units in Switzerland, 2023, for grocery and logistics firms. US, pilot programs in California with first element fuel stations. Advantages, ideal for long-haul routes and cold climates, no range loss in winter. Zero emissions, only water vapor byproduct. Challenges, hydrogen cost, $16/kg, versus diesel's $4.50/gallon equivalent. Infrastructure, only 60 public hydrogen stations in the U.S., 2023. Competitors, Nikola TREFC EV, 500-mile range, targeting ports and heavy-duty freight. Toyota-Isuzu partnership, developing hydrogen trucks for Japanese markets. Comparative analysis metric battery electric trucks hydrogen fuel cell trucks range 150-500 miles 300-500 plus miles refuel/recharge time 30 mins 8 hours 8:20 minutes infrastructure growing, Tesla, CCS, Limited, Global Gaps, best use case short/regional hauls long haul, heavy freight challenges and opportunities, battery electric, grid strain, charging 10 semis requires 10 MW equivalent to a small town. Mining impacts, lithium and cobalt sourcing raises ethical concerns. Hydrogen, green H production, only 0.1% of hydrogen is green, via renewables, most is gray, from methane. Policy support, EU's hydrogen strategy and US Inflation Reduction Act subsidies, $3/kg tax credit. Chapter summary electric trucks like the Tesla Semi and Rivian's Amazon fleet are decarbonizing last mile and regional logistics, while hydrogen fuel cell trucks, e.g., Hyundai Scient, target long-haul freight. Both face hurdles charging infrastructure for electric, green hydrogen scarcity for fuel cells but offer complementary paths to sustainable freight. As battery costs drop and hydrogen tech scales, these innovations could eliminate 1.5 gigatons of annual CO by 2050, transforming the backbone of global commerce. Next, Chapter 8 explores micromobility, e-scooters, e-bikes, and green public transit solutions. Chapter 7, Sustainable Ground Transportation 7.2 Micromobility, e-scooters, e-bikes, and shared systems micromobility solutions are transforming urban transportation by offering low-carbon, flexible alternatives for short trips. E-scooters, key players, Lime and Bird, deploy dockless e-scooters in 200-plus cities globally, e.g., Paris, Los Angeles. Voi, Europe partners with cities to enforce geofencing and speed limits. Benefits, emission reduction, replaces car trips under 3 miles, cutting CO by 0.5 kg per ride. Cost, $1.13 per ride versus $10.15 for ride-hailing. Challenges, safety, 40% of injuries involve first-time riders, CDC, 2023, Cities like Barcelona mandate helmets. Clutter, improper parking prompts bans, e.g., Paris 2023 referendum to limit operators. E-bikes, market growth, sales surged by 240% from 2019-2023, led by brands like Rad Power Bikes and Van Moof. Cargo e-bikes, used by UPS and DHL for last-mile deliveries in cities like London. Policy support, subsidies, France offers €500 4,000 rebates, California's $10 million e-bike voucher program. Impact, replaces 21% of car trips in cities with robust bike lanes, Amsterdam, Copenhagen. Shared systems, bike sharing, City Bike, NYC 25,000 bikes, 150 million rides since 2013. Mobike, China pioneered dockless tech before regulatory crackdowns. Integration with transit, London, Oyster cards unlock Santander cycles. Chicago, Divvy e-bikes linked to Metro Transit app. 7.3 Green public transit, electric buses and solar-powered ferries. Electric buses, global leaders, Shenzhen, China, 16,000 electric buses, 100% of fleet, since 2017, reducing CO by 1.35 million tons/year. Los Angeles Metro, targets 100% electric fleet by 2030, 50 bid buses deployed in 2023. Technology, battery swapping, Blink charging pilots 5-minute swaps in Maryland. Wireless charging, Electrian's inductive lanes tested in Tel Aviv and Detroit. Challenges, grid demand, charging 100 buses requires 30 MW, power for 20,000 homes. Cold weather, range drops 30–50% in cities like Oslo and Montreal. Solar-powered ferries, innovations, MS Turiner Planet Solar, Switzerland first solar-powered vessel to circumnavigate the globe, 2012. Kerala, India, Aditya, the world's first solar ferry, 2016, transports 75 passengers using 140 rooftop panels. Benefits, zero emissions, replaces diesel ferries emitting 0.5 kg CO per passenger mile. Low O&M costs, solar ferries cut fuel expenses by 80%, Kerala's experience. Challenges, space limitations, solar panels cover large areas, reducing passenger capacity. Weather dependency, cloudy regions require hybrid systems, solar and battery. Case study, Norway's green transit ecosystem, electric ferries, Medstrom, 2022, the world's first zero-emission fast ferry, connects Stavanger Islands. E-bus integration, Oslo's electric buses charge via hydro-powered grids, achieving 95% renewable energy use. Chapter summary. Micromobility and green public transit are cornerstones of sustainable cities. E-scooters and e-bikes reduce car dependency for short trips, while electric buses and solar ferries decarbonize mass transit. Challenges like infrastructure gaps and energy storage persist, but innovations in battery tech, policy incentives, and public-private partnerships, e.g., city bikes expansion, signal progress. As cities prioritize climate goals, these solutions will play pivotal roles in achieving net zero mobility. Key takeaways: micromobility balances convenience with regulatory growing pains, safety, parking. Electric buses, dominated by China but expanding globally with battery swap and wireless charging tech. Solar ferries, niche but impactful, especially in archipelagos and sunny climates. Next, Chapter 8 examines policy and infrastructure challenges in scaling sustainable transport globally. Chapter 8, Policy and Infrastructure Challenges. The transition to sustainable transportation hinges on overcoming regulatory fragmentation, infrastructure gaps, and global inequities. This chapter dissects the policy frameworks and logistical hurdles shaping the future of mobility, from EV adoption to hydrogen highways and equitable access. 8.1 Government regulations. EV subsidies and airspace management. EV subsidies. Governments use financial incentives to accelerate EV adoption, but approaches vary widely. U.S. Inflation Reduction Act, 2022 offers up to $7,500 tax credits for EVs with domestically sourced batteries, disadvantaging foreign automakers like Hyundai. EU CO standards, fines automakers exceeding 95 gram CO/km, 2023, pushing brands like Volkswagen to phase out ICE by 2035. China's NEV mandate requires automakers to produce 40% EVs by 2030, with subsidies favoring local giants like BID. Challenges, trade tensions, EU disputes over IRAs by American clauses. Fraud risks, South Korea's 2023 scandal involving $32 million in fake EV subsidies. Airspace management integrating drones and eVTOLs into urban skies demands new regulatory frameworks. FAA's UASFM, 2023 expands drone corridors for Amazon Prime Air and Zipline medical deliveries. EASA's USpace, Europe's digital air traffic system for eVTOLs, tested in cities like Paris and Munich. Conflict zones, drones disrupting commercial flights, e.g., Gatwick Airport shut down in 2018. Case study, Los Angeles Urban Air Mobility Partnership, 2023, coordinates eVTOL routes with SpaceX satellite data to avoid airspace clashes. 8.2 Building charging and hydrogen refueling networks. EV charging infrastructure, progress, Tesla Supercharger Network, 45,000 plus global stalls, 2023, now open to Ford/GM EVs via NACS adapters. EU's AFIR regulation, mandates fast chargers every 60 km on highways by 2025. Challenges, grid upgrades. A single 350 kilowatts charger draws power equivalent to 50 homes. Texas's 2023 heatwave caused charging blackouts. Rural gaps, only 5% of U.S. rural counties have fast chargers, DOE, 2023. Hydrogen refueling networks, current state, California, 60 stations, 2023, serving 12,000 FCEVs. Germany, H2 Mobility's 130 stations target 300 by 2030. Barriers, cost, $2 million per station versus $100,000 for a fast charger. Chicken and egg dilemma, Hyundai Scion trucks in Switzerland rely on temporary mobile stations. Innovations, Hyundai's hydrogen highway, deploying mobile refuelers along European freight corridors. Shell's green H-hubs, CO located with wind farms in the North Sea. 8.3 Global equity, access to advanced mobility in developing nations. Disparities in EV adoption. Norway, 90% of new cars sold are EVs, 2023, due to tax exemptions and free charging. Africa, only 0.3% of vehicles are electric, hindered by high costs, e.g., a Tesla Model 3 costs $75,000 in Kenya due to tariffs. Solutions and challenges, localized innovation. Basigo, Kenya electric buses assembled locally using BID kits, cutting costs by 30%. Solar e-rickshaws, India 1.5 million deployed, reducing reliance on lead-acid batteries. Ethical concerns, battery waste, Europe exports 70% of used EV batteries to Africa, lacking recycling safeguards. Neocolonial tech, Western eVTOLs may bypass local needs, e.g., Nairobi's priority is paved roads, not air taxis. Case study, UN Solutions and Program trains engineers in Vietnam and Colombia to build EV supply chains using regional materials, e.g., Bolivian lithium. Chapter Summary. Sustainable transportation success hinges on harmonizing policy, infrastructure, and equity. While the global north races toward electrification and air taxis, developing nations risk being sidelined without tailored solutions. Bridging these gaps requires collaborative governance, aligning subsidies and airspace rules across borders. Infrastructure justice, prioritizing affordable charging in rural and low-income areas. Ethical tech transfer, avoiding green colonialism by empowering local innovation. Key takeaways: regulations must balance innovation with safety and equity, e.g., IRA's domestic bias versus global climate goals. Infrastructure, hydrogen and EV networks need massive public-private investment. Equity, solar micromobility and localized EV assembly can leapfrog legacy systems. Next, Chapter 9 explores the business dynamics of future mobility, from startups to legacy automakers. 9. The business of future mobility. 9.1 Startups versus legacy automakers. Key dynamics: startups, e.g., Lucid, Rivian, NIO agile, innovative, niche-focused, but face scaling challenges and funding dependency. Legacy automakers, e.g., GM, Ford leverage manufacturing scale and brand trust but must navigate transition costs and cultural inertia. 9.1.1 Startup innovations. Lucid Motors, targets luxury segment with high-efficiency batteries, e.g., Lucid Air's 500-plus mile range. Rivian focuses on adventure EVs, R1T truck, R1S SUV, and B2B deals. Amazon electric vans. NIO differentiates with battery swapping stations, power swap, and premium user experiences. NIO houses challenges: production scalability, supply chain stability, and path to profitability. 9.1.2 Legacy automakers EV transition. GM's Ultium platform, modular battery system enabling diverse EVs, Hummer EV, Cadillac Lyriq, aims for cost efficiency and flexibility. Ford's EV pivot, leverages iconic brands, Mustang Mach-E, F-150 Lightning, to attract traditional buyers. Challenges: retooling factories, managing union labor, and balancing ICE phase-outs with EV investments. 9.2 Venture capital trends in transportation tech. Key areas: battery tech, solid-state, recycling, autonomous driving, charging infrastructure, and micromobility, e.g., Bird, Lime. Notable trends: megarounds, Rivian's $10.5 billion pre-IPO funding, 2021. SPACs, used by Lucid and others to go public rapidly. Corporate partnerships, legacy automakers investing in startups, e.g., Ford's stake in Rivian. Drivers, government incentives, tax credits, infrastructure bills, and sustainability-focused funds. 9.3 Marketing strategies, overcoming barriers, range anxiety solutions, infrastructure, Tesla supercharger network, GM's Ultium Charge 360 partnerships. Technology, NIO's battery swaps, Lucid's extended range claims. Tech skepticism mitigation, education, Ford's EV Myths campaigns, interactive test drives. Ecosystem integration, smart home charging, Tesla Powerwall, subscription models, Volvo's Care by Volvo. Trust building, warranties, e.g., Hyundai's 10-year battery warranty, celebrity endorsements and user communities, NIO's fan events. Cross-sectional insights, VC influence, fuels startup R&D, e.g., Rivian's IP, while legacy firms use capital to retool, GM's $35 billion EV pledge. Policy impact, infrastructure grants and emissions regulations accelerate both startup and legacy strategies. Future outlook, collaboration, startup innovation and legacy scale, likely to dominate, with sustainability as a unifying goal. This structured analysis highlights competitive strategies, investment trends, and consumer-centric approaches shaping the future mobility landscape. 10 Future Horizons, 2040 and beyond. 10.1 Hydrogen-powered aviation and transonic flight. Overview: hydrogen emerges as a sustainable alternative to jet fuel, targeting decarbonization of aviation. Technologies: hydrogen fuel cells, for electric propulsion, e.g., ZeroAvia's regional aircraft. Liquid hydrogen combustion, Airbus ZEROe concepts for long-haul transonic flights, Mach 0.8-0.9. Key players, Airbus, Zero Avia, Universal Hydrogen. Challenges, technical, cryogenic storage, energy density trade-offs, and retrofitting existing aircraft. Infrastructure, hydrogen production, green H via electrolysis, refueling networks at airports. Regulatory, safety certifications, FAA, EASA, international standards for hydrogen handling. Future outlook, short-haul hydrogen flights by 2035, transonic hydrogen jets for intercontinental routes by 2040. 10.2 Autonomous cargo ships and drone delivery networks. Overview, AI-driven logistics reshape global freight and last-mile delivery. Technologies, autonomous ships, Rolls-Royce's Intelligent Awareness Systems, Yara Birkeland, world's first electric autonomous container ship. Drone networks, Amazon Prime Air, Wing, Alphabet, and Ziplin's medical delivery drones. Key players, Maersk, Kongsberg Maritime, Amazon, DJI. Challenges, regulatory, maritime law updates, IMO, drone airspace management, FAA, EASA. Operational, cybersecurity risks, collision avoidance algorithms, battery/payload limits. Societal, job displacement in shipping, noise pollution, and public trust. Future outlook, autonomous ships dominate fixed routes, e.g., coastal freight, by 2040. Urban drone hubs integrated with smart city infrastructure, rural delivery remains limited. 10.3 Integration of AI, IoT, and smart city ecosystems. Overview, seamless connectivity between mobility, energy, and urban services. Technologies, AI-driven traffic management, adaptive traffic lights, e.g., Pittsburgh SurTrack, predictive maintenance. IoT sensors, real-time air quality monitoring, smart parking and electric vehicle, EV, charging optimization. Mobility as a service, MaaS platforms like WIM, Helsinki, integrate public transit, scooters, and ride-sharing. Key players, Siemens, Cisco, Sidewalk Labs, and City Initiatives, Singapore, Barcelona. Challenges, data privacy, GDPR compliance, anonymization of citizen data. Interoperability, unified standards for cross-vendor systems. Equity, ensuring low-income access to tech-driven services. Future outlook, AI-optimized cities reduce emissions by 30–50% through efficient routing and energy use. 5G/6G networks enable real-time vehicle-to-everything, V2X, communication by 2040. Cross-sectional insights, sustainability synergies, hydrogen aviation and smart grids share renewable energy infrastructure, autonomous logistics reduce empty miles. Policy drivers, carbon-neutral mandates, e.g., EU Fit for 55, accelerate R&D, public-private partnerships fund pilot cities. Human-centric design, ethical AI frameworks and community engagement critical for equitable adoption. Conclusion, by 2040, mobility converges on sustainability, autonomy, and hyperconnectivity. Hydrogen and AI redefine speed and efficiency, while smart cities prioritize livability. Challenges remain, but collaboration across tech, policy, and society will unlock this future. 11 Conclusion, toward equitable and sustainable mobility. 11.1 Balancing innovation with environmental justice. Key challenges, resource extraction, mining for lithium, cobalt, and rare earth metals often occurs in marginalized communities, causing ecological harm, e.g., Congo's cobalt mines. Infrastructure gaps, EV charging deserts in low-income/rural areas, autonomous vehicle services may prioritize affluent urban zones. Emissions burden, legacy pollution from highways and ports disproportionately impacts communities of color, e.g., California's diesel death zones. Solutions, policy-driven equity, mandate inclusive zoning, e.g., California's SB 1000, and fund charging infrastructure in underserved areas. Community CO design, involve local stakeholders in mobility planning, e.g., Los Angeles * Green New Deal for transportation. Circular economy, battery recycling programs, redwood materials, and ethical sourcing certifications, Fair Cobalt Alliance. 11.2 Educating the workforce of tomorrow, transition risks, job displacement. 3M auto workers globally face retraining as ICE manufacturing declines, e.g., Ford's $30 billion EV shift by 2025. Skill gaps, demand for AI engineers, battery chemists, and EV technicians outpaces supply. Strategies, public-private partnerships, Germany's auto industry 4.0, vocational training in EV assembly and software integration. Tesla's Gigafactory academies, partner with community colleges for battery production training. Upskilling programs, UAW Ford National Program, retrain 58,000 workers in EV and software roles. Online platforms, Coursera's Future of Transportation Nanodegrees. Global South Inclusion, invest in solar-powered microgrid training in Africa for local EV infrastructure. 11.3 Global collaboration for zero-emission transport, barriers, economic disparities, high EV costs in developing nations, e.g., average EV price equals 50x Ghana's GDP per capita. Policy fragmentation, inconsistent emissions standards, e.g., EU versus ASEAN regulations. Tech access, patents and supply chains controlled by a few nations, China's 70% battery production dominance. Pathways, multilateral agreements, Global Battery Alliance, standardize ethical mining and recycling across 70+ countries. 28 Colombian pesos transport pledge, accelerate zero-emission vehicle adoption in signatory nations. Tech transfer initiatives, UN's * Sustainable Mobility for All, share open source EV designs, e.g., OSVehicles modular platforms. South-South collaboration, India's Tata Motors partners with Kenya to produce affordable EVs. Financing mechanisms, World Bank's $200 billion climate fund, subsidize electric buses in Latin America and Southeast Asia. Carbon credits for mobility, reward companies deploying EVs in low-income regions, e.g., Blusmart in India. Cross-sectional insights, equity as innovation catalyst, inclusive policies, e.g., U.S. Justice 40 initiative, ensure marginalized groups benefit from clean transit. Education bridges gaps, reskilling reduces resistance to change, fostering social acceptance of AI and automation. Collaboration over competition, shared R&D, e.g., EU's Battery 2030 End project, accelerates breakthroughs while reducing costs. Final perspective, achieving equitable and sustainable mobility by 2040 demands more than technology, it requires systemic empathy. From cobalt mines to coding bootcamps, every link in the chain must prioritize people and planet. The roadmap is clear: innovate responsibly, educate inclusively, and collaborate relentlessly. Success hinges on treating mobility not as a commodity, but as a fundamental right. Appendices - Timeline of key transportation milestones, 2020-23, 2000, Toyota Prius launches as the first mass-produced hybrid vehicle, popularizing electrification. 2003, Tesla Motors founded by Martin Eberhard and Mark Tarpenning, Elon Musk joins in 2004. 2008, Tesla Roadster debuts as the first highway-legal electric car with lithium-ion batteries. 2009, Google starts its self-driving car project, later Waymo. 2010, Nissan Leaf becomes the world's first mass-market BEV, Uber launches ride-hailing in San Francisco. 2012, Tesla Model S redefines luxury EVs with over 300-mile range. 2013, Elon Musk publishes the Hyperloop Alpha white paper, BID becomes the world's largest EV maker. 2015, Paris Agreement accelerates global decarbonization goals, Tesla Autopilot debuts. 2016, Waymo spins off as a standalone Alphabet company, Volvo pledges to phase out ICE by 2030. 2017, Hyperloop 1 completes first full-scale test in Nevada, China surpasses 1 million EV sales. 2018, EU mandates CO emission cuts for automakers, Rivian unveils R1T electric pickup. 2020, Tesla hits $1 trillion valuation, EU announces Fit for 55 plan to cut transport emissions by 55% by 2030. 2021, Lucid Motors goes public via SPAC, Ford unveils F-150 Lightning. 2022, EU votes to ban ICE vehicle sales by 2035, CATL unveils sodium-ion batteries for cheaper EVs. 2023, Tesla Cybertruck enters production, China's bid overtakes Tesla in global EV sales. Glossary of technical terms, ADAS, Advanced Driver Assistance System sensors and software, e.g., adaptive cruise control, lane keeping, that enhance vehicle safety, BEV, battery electric vehicle fully electric vehicle powered solely by a battery, e.g., Tesla Model 3, eVTOL, electric vertical takeoff and landing electric aircraft for urban air mobility, e.g., Joby Aviation, LiDAR, light detection and ranging, laser-based sensing for autonomous vehicles. Maglev, magnetic levitation high-speed trains levitated and propelled by magnetic forces, e.g., Shanghai Transrapid, MOS, mobility as a service integrated platforms for multimodal transit, e.g., Uber, WIM, solid-state battery, next-gen battery with solid electrolytes for higher energy density and safety. V2X, vehicle-to-everything communication between vehicles and infrastructure, e.g., traffic lights, pedestrians, ZEV, zero-emission vehicles with no tailpipe emissions, BEVs, hydrogen fuel cell cars. Profiles of leading companies and innovators. Companies, Tesla, pioneer in EVs and autonomy, led by Elon Musk. Key products, Model 3, Cybertruck, Supercharger Network. Rivian, adventure-focused EV startup, CEO RJ Scaringe. Key products, R1T truck, Amazon electric delivery vans. NIO, Chinese EV maker known for battery swapping, founder William Li. Key Tech, power swap stations, NIO houses. Waymo, Alphabet's autonomous driving unit, CEO Tekadra Mawakana. Key project, Waymo One robo-taxi service. Bid, world's largest EV manufacturer, Warren Buffett backed. Dominates buses and low-cost EVs. Zoix, Amazon-owned startup developing fully autonomous, purpose-built robo-taxis. Innovators, Elon Musk, Tesla, SpaceX, Hyperloop revolutionized EVs and reusable rockets. Mary Barra, GM led GM's Ultium platform and $35 billion EV investment. Jens Stoltenberg, Yara International backed the world's first autonomous electric cargo ship, Yara Bergland. Olaf Scholz, German Chancellor championed Germany's auto industry 4.0 workforce retraining initiative. Anastasia Len, CEO of Electric Hydrogen advancing green hydrogen for heavy transport. Note, these appendices provide foundational context for understanding the technological, economic, and social shifts in mobility. For deeper analysis, cross-reference with chapters on policy, Section 5, and equity, Section 11.